The concavity of the graph of a function is the notion of curving upward or downward. Now, before I discuss this in detail, I just want to go through some key points that will help us to understand the idea behind the concavity of functions. We had discussed in previous videos that the first derivative of a quadratic is a linear function. So we had discussed that the first derivative of a quadratic function is a linear. So what this means is if I have a quadratic function, like for example, f of x is equal to 2x squared plus 3x minus 4. Now remember, this is a quadratic. If I find the first derivative, okay, of this function, what I'll end up with is a linear function. And this idea can help us to sketch derivatives of functions. Okay, they can help us to sketch a derivative. For example, if I have a quadratic function, I can be able to sketch its derivative because I know that its derivative will be a linear based on this idea. So it makes it easier to sketch derivatives of functions. Okay, so I'll go back to where we were. So here we have two functions. And what I want to do is I want to start by sketching derivatives of these functions. Now, I'll start by labeling the axis. This is y, that is x. This function here is, and this one as well, is y is equals to f of x. These are the original functions, okay? That's y. This is x as well. Now, what I want to do here is, this goes by the way to infinity. So what I want to do here is to sketch the derivatives of these functions. So let me start from the left-hand side. I know that the slope at this point, will be 0. So the slope at that point will be 0. So I can mark that point there. The slope at this point is positive because you're going uphill, which means it can be somewhere here, positive. The slope at this point here will be negative, which means it will be somewhere below there. Now, if I join these points using a straight line, what I'll end up with is a linear function. And it makes sense because we know that the derivative of a quadratic is a linear function. So this function here basically represents the derivative of the original function. So this one here is y is equals to f dash x. That's the graph representing the first derivative of a quadratic function. Now we can do the same thing on the other side. So we know that the slope at this point is 0. Okay, the slope at this point is negative, so we can put it somewhere here. And the slope at this point is positive, which means it could be somewhere there. And then we can join these 3 points using a straight line. Okay. And what we end up with is the graph of the first derivative of this function. Okay. So this graph here is the graph of y is equals to f dash x. Okay. Let's look at some key points that will help us to gain even a deeper understanding of what's really happening here. So, small space on there. So, On the left, what we notice is that as we move across from left to right, the gradient of the slope is decreasing. Okay, as we move from left to right, the slope is decreasing, and you can see the slope of this straight line. It's actually decreasing. Okay, from positive to negative. So we can say that from the left, as we move across from left to right, um, the slope is decreasing. We can generalize this using a mathematical notation. We can say that the slope of the slope, okay, we can say that the slope of the slope is less than 0, okay, which means that the gradient of this straight line will be negative, which means it's less than 0. Um, this is now from the definition of concavity. A curve where the gradient is decreasing is said to be concave downwards. Okay, so a curve where the gradient is decreasing is said to be concave downwards. Now, I've introduced a new word here, concave downward. This is just a mathematical description of what's happening here, okay? So, if we have a situation whereby the gradient of a curve is decreasing, then it is said that the curve is concave downwards, like what we have here. So we can generalize this statement in general and say that if the second derivative is less than 0 on a given interval, then the graph of a function is concave downward on that interval. Okay, so we can say if the second derivative is less than 0 on a given interval, then the graph of the function is concave downward on that interval. So that final statement summarizes the two statements that we have here. Now we can do the same thing on the right hand side. Okay, on the right hand side we can see that as we move across from left to right, the slope is increasing, okay, from negative to positive. So we can generalize and say that hence the slope of the slope, in fact, if you look at the straight line above here, you can notice that the slope of that straight line will be greater than 0. So hence we can generalize this using a mathematical statement and say that hence the gradient of the gradient will be greater than 0. So in mathematics, a curve where the gradient is increasing is said to be concave upward. Okay, so a curve whereby where the gradient is increasing is said to be concave upward. Okay, so remember on the left we discussed about concave downwards when and that happens when the gradient is decreasing. But when the gradient is increasing, then the curve is said to be concave upward. So we can put these two statements together and generalize and say that if the gradient of the gradient, or if the slope of the slope is greater than zero, is greater than zero on any given interval, then the graph of a function is concave upward on that interval. What I mean by that is this. Here on the left we said this is concave downward because the slope of the slope, or the slope of the straight line, is less than zero. But what you are saying here is that if the slope of the slope, or the slope of this straight line, okay, the slope of the gradient, is greater than zero, then the function is said to be, or the curve is said to be concave upward. Okay, so let's generalize this in a statement below here. So we can say that if the slope of the slope is greater than zero on a given interval, okay, so that's the difference between concave downwards and concave upwards. Okay, and it all depends on the signs of the second derivative.